All right. Hey, everyone. So today we're going to be talking about graphs of polar equations. Hopefully you have this page of notes. If not, make sure you go and get one of those from the orange folder over on the shelf. If you're in my classroom, of course. If you're not in my classroom, well, then you can follow along here. All right, so on my screen, I have both the notes and a window of Desmos. You can also use a TI-84 or something like that, any other graphing calculator for this. I'll probably try to show both, but we're going to go through a little bit of exploration on graphs of polar coordinates. So let's get started. Um, so first off, the differences between a Cartesian or a normal grid that we're used to seeing and a polar grid. First off, the origin is now called the pole. The positive x-axis is now called the polar axis, and the y-axis is now the line theta equals pi over 2. So that's kind of how we want to orient ourselves here. So for this first example, we're going to sketch the graph of the polar equation r equals 4, and then convert it to an equivalent rectangular equation. Now, we've seen this one in class before. So if we draw ourselves a polar grid, we know r equals 4 is the place where, or is the collection of points that are 4 units away from the pole. And that actually, it makes a circle of radius 4, centered at the pole. And so we've seen this one before. If we were to graph it on our graphing calculator, you can just type r equals 4, and it shows you the circle that we're talking about. So we can just kind of draw ourselves a circle here. We know that these are both positive 4. If you were graphing in Cartesian coordinates, these would be negative 4s. And then if we were going to convert this into a rectangular equation, well, if we know equations very well, we know that a circle is x squared plus y squared equals r squared, where r is the radius. So this particular circle would be x squared plus y squared equals 16. But if we were going to do it with the converting rectangular and polar kind of method, we know that r is equal to the square root of x squared plus y squared. So we can take and replace r with that. And then we could square both sides. And we get the equation x squared plus y squared equals 16. So that would be the equivalent rectangular equation. All right. So pretty simple to start off with. We're just looking at a circle with a given radius. So let's go to the next one. This time we are going to sketch the graph of theta equals negative 4 pi over 3. So if we think about, again, our polar grid, if this starts off with theta equals 0 here, and we're going to negative 4 pi over 3, I find it easier to think in positive radians especially. So negative 4 pi over 3 is the same as positive 2 pi over 3, because you can just add 2 pi to it and get the same angle, right? So if I add 2 pi to this, we get 2 pi over 3, and I know where that angle is a little bit better because of the unit circle, right? So we know that that angle, like that one right there. So if theta is always that angle, what we're talking about is this line here. And so if we were to convert it into an equivalent rectangular equation, we know we have theta equals negative 4 pi thirds. If you take tangent of both sides, you get tangent theta equals tangent of negative 4 pi thirds. Well, tangent of negative 4 pi thirds is negative root 3. And also, we know that tangent theta is y over x. When we were dealing with converting polar and rectangular, this is something we used a lot. So I can replace tangent theta with y over x. And then I can multiply x on both sides to get y equals negative root 3 x. And this would be my equivalent rectangular equation. And it does represent our graph here. You can even go and graph it here just to check. Or maybe you can't. Desmos, can you not? Aw, sad. Okay, you can't really do that on the TI, I guess, either. Anyways, so that's why it's important to also be able to sketch it, right? Anyways, let's go ahead and move on to the next one, because, you know, these are fun and all, but there's lots more interesting equations out there that we can use. All right, example 3's got a lot of equations for us here. Sketch the graph of the polar equation, r equals 3 cosine theta, to start with. So 3 cosine theta. All right. We got a circle. And the interesting thing about this circle is that it does go through the pole, but it's not centered at the pole like our last circle was. And it looks like the diameter is 3. So let's draw our circle. The diameter is 3. And it hits the pole, but it does not center at the pole. All right. Predict what you think the graph of r equals 5 cosine theta, r equals 8 cosine theta, and r equals negative 4 cosine theta will look like. All right, pause the video real quick and see if you can predict what you think those graphs are going to look like based on what the graph of this one looked like. All right, hopefully you paused the video and then came back. Let's explore what those look like real quick. If I were, you know, predicting and didn't know, but noticed that 3 corresponded to the diameter here, I think I would also guess that for 5 cosine theta, the diameter will probably also be 5 and it will look similar. And that 8 cosine theta, something similar will happen there as well, and that the diameter would be 8. We can check that really quick. Let's just copy this here, but make it a 5. And then an 8. So now look at that. Perfect. Our prediction came true. We get circles that still hit the pole, but they're not centered at the pole. And they have a diameter of whatever number is in front. Let's try, did anyone, hopefully you thought about negative 4 cosine theta as well. Let's see what that looks like. You might notice it just does the same thing, but on the other side, kind of in negative land, if you're thinking about things in the Cartesian plane. So it gives us, that's a terrible circle, but we get the idea. A circle where you go 4 units in that direction instead for your diameter. Okay, so let's generalize this a little bit. What do we think for r equals 2a cosine theta and 2a sine theta? Do we think sine is going to affect it at all? Spoiler alert, it does. If we make this sine instead of cosine, notice how it does the same thing, except it orients it along what would in Cartesian coordinates be the y-axis, or along in polar coordinates, the line theta equals pi over 2. So kind of along that idea here, we have a nice summary of what happens with things in the format of 2a cosine theta or 2a sine theta. They are circles centered off the pole, but they do go through the pole with a radius of a. So the reason that we have the 2a is because the numbers in front define the diameter, but usually we like to think of circles in terms of the radius instead. So a would be the radius. So whatever number total is in front of your sine or your cosine, divide it by 2, and you get the radius. Anyways, graphs involving cosine are going to have symmetry on the polar axis or the x-axis in Cartesian coordinates. And graphs involving sine are going to have symmetry along the y-axis, or the line theta equals pi over 2, kind of like we talked about. If a is greater than 0, you end up with graphs along the positive x-axis or the positive y-axis. If you end up with a less than 0, you're going to get graphs on the negative x-axis or the negative y-axis. Hopefully kind of the way we would expect. All right, so that's one type of polar graph that you're going to see quite often. Another common polar graph is going to be things that take the format of the ones in example 4. So let's get some new graphs going here. Also, if you're graphing things on a TI calculator, real quick, if you go to mode, make sure that you're in polar mode and radian mode, and then go to y equals, and you can also graph things in terms of r and theta there. So like with this next one, if I do 3 minus 3 sine theta, and then I hit graph, oops, my window is too small. I went 0 to pi. For these, you're going to have to go 0 to 2 pi. And we get the same kind of curve that we'll get on Desmos. I'm going to have us keep using Desmos because it's a little bit easier to see on the video. 3 minus 3 sine theta. All right. So let's look at some of the points along here. You might notice that, let's see, we touch the pole here at -3 and at +3. We cross the either the polar axis or the x-axis, and down here at -6 we also cross this line, or the y-axis. So those are all important observations here that have to do with the numbers from this graph. So let's sketch it really quick. All right, so we know this has to go out, and these graphs aren't going to be super pretty. Do your best. Let's see, so we do something like that. All right, and the ones graphed on Desmos always look much prettier than mine, but there we go. We get the idea. All right, so that's 3 minus 3 sine theta. Let's try a different one. 4 plus 4 sine theta. All right, we got to zoom out a little bit here because we know that, all right, these are going out to 4 and -4. It's also flipped over. There's a lot going on here. And then this is up here at 8. All right, well, let's sketch that one too. Let's see, so we know these may not be perfectly to scale, but here we go. That's 8, that's 4, that's -4. We know this graph is going to look something like this, although hopefully a little bit more symmetrical. And we may want to label our graphs. This was 4 plus 4 sine theta. This was 3 minus 3 sine theta. Okay. Kind of looks like a heart, right? Or at least one of them does. Let's do another one. 2 plus 2 cosine theta. All right, let's turn off some of the others so that we get a better picture of what's going on. Nice. Okay, so we've got 2 and 2, and then 4. Hopefully we're kind of starting to notice a pattern. These were 4, 4, and 8. This was 3, 3, and 6. This is now 2, 2, and 4. It's also oriented sideways, kind of the way we would expect a cosine graph at this point to be oriented. So we have 2, 2, and 4. And this was 2 plus 2 cosine theta. All right, we got 2 more here. we have 2 minus 2 cosine theta. And then we have negative 2 minus 2 cosine theta. But wait a minute, those ones overlap. So as you can see on the graph now, these two are the same graph, or they're traced out in the same location at least. So for this one, we get it going the opposite direction. So we got 2 and negative 2 still, but this time going like that, and then this will be at negative 4. And there we go. All right, so these graphs all look very similar to one another, and their equations also look pretty darn similar to one another. Let's go ahead and turn the page and see if we can generalize something here. All right, graphs that are taking the format of r equals a plus or minus a cosine theta and r equals a plus or minus a sine theta are all called cardioids. They kind of look like hearts, right? And so anyways, it's important that these two numbers be the same. The constant and the coefficient in front of sine or cosine are the same as each other. Graphs involving cosine are going to have polar axis symmetry. Graphs involving sine are going to have symmetry along the y-axis, or the theta equals pi over 2 line. And so that's another important family of polar functions. All right. So we've got one more family of polar functions that we're going to talk about today. The last family of polar functions is going to start with example 5 here. So we're going to see if we can generalize a few more things. So let's get rid of our old equations and start with some new ones. This time we're going to look at r equals 3 minus 4 sine theta. All right, well, we get this kind of loopy looking thing here. Some things we should notice about our loopy looking thing. First off, that loop goes from 0 to negative 1. That's an important feature. It crosses here at negative 3, and over here it crosses at positive 3. And then down here looks like we cross negative 7. So those are all important things to notice here. Let's go ahead and sketch the graph of our first one, 3 minus 4 sine theta. So we know the loopy part goes from 0 to negative 1. We know that we cross here at 3 and negative 3, and down here at negative 7. So the rest of our graph is going to look something like that. All right, it's also important to note that all the graphs we've looked at so far fully trace out in 0 to 2 pi. So Desmos automatically traces it out all the way for us, but if I only traced out 0 to pi, it would only draw part of my graph. So these are other kind of interesting things to note. If I went from 0 to 4 pi, it would trace my graph twice. But anyways, there we go, 3 minus 4 sine theta. And hopefully we're already kind of starting to notice some things that happen numerically. Like, is it a coincidence that these are 3s? Probably not. Is it a coincidence that this that we cross at negative 7 down here or at negative 1 here? Probably not. The difference between 3 and 4 is 1, right? And the difference between, or the sum of 3 and 4 is 7. That might have something to do with it if we're thinking kind of, you know, conjecturing what might happen with the next one. So let's see if our prediction holds. Let's graph another. This time we're going to go 3 minus 5 sine theta. And would you look at that? We end up, we're still crossing here at negative 3 and positive 3. But now the loopy part goes down to 2. And the whole thing goes down to negative 8. So that's probably not a coincidence. Let's graph this one as well. And then we'll see if we can make any other predictions. So we're still going -3 to 3. This time the loopy part goes down to -2. And the body, or the rest of it, goes down to -8. All right, so let's sketch. We've got the loopy part. And then we have the rest of it that looks a lot like our cardioids. All right. Let's try another. It said 2 minus 5 sine theta for the next one. So 2 and 5. And as we would hopefully expect at this point, we got, let's see, the loopy part goes down to 3, which makes sense. The difference between 5 and 2 is 3. This time, we cross here on the polar axis at -2 and +2, which hopefully is now something that we could kind of predict because this number is a 2. And let's see, we cross down here at -7, which tracks because 2 and 5 is 7. So yeah, we can kind of start seeing some of the things that impact our different polar graphs. What do we think would happen if we change it to a cosine? Would it just flip it sideways again? Probably. Let's try it. Let's go with this one, and we're going to make it a cosine instead. And yep, lo and behold, it flips it sideways when we make it a cosine. So maybe we want to note that real quick. If we did 3 minus 4 cosine theta, it's probably going to look, or we know it looks, something like this. Three minus 4 cosine theta. This one was 3 minus 5 sine theta. This one was 3 minus 4 sine theta. All right. Let's see. Let's try some of the others. Let's see, negative. So we know these will pretty much look like the way that these ones did, but sideways. Let's try the 3 plus 4 sine theta. Let's change this to a plus. And it flips it over. Kind of hopefully how we expect at this point. Or -3 plus 4 sine theta. The same thing that happened with the cardioid when we changed this from a positive to a negative. Nothing. All right. So this is yet another family of functions. They all look like this with their little loop in the middle. These are called limisones with the funny French C thing. So graphs where we have a plus b cosine theta or a plus b sine theta, where b is greater than a. These are all going to be called limisones. They are traced out once counterclockwise from 0 to 2 pi. So that's how long it takes to trace it out. Let's see, graphs involving cosine, again, are going to have x-axis or polar axis symmetry. Graphs involving sine are going to have symmetry along theta equals pi over 2, or the y-axis. The diameter of the outer loop, so like from the pole down all the way down to the bottom of the outer loop, is going to be the sum of b and a if you use absolute value of b plus absolute value of a. And then the diameter of the inner loop, so from the pole to the bottom of the inner loop, is going to be absolute value of b minus absolute value of a. Kind of how we started noticing, right? And then, let's see, what else we got here? The values for which r equals 0 are called polar zeros. So, you know how we find zeros of functions in Cartesian coordinates or rectangular coordinates? We find the places where y is 0. When we're doing polar zeros, we find the places where r is 0. And knowing the angles that these happen at is really important, especially if you're going to try to sketch a function by hand. Yeah, you want to find these prior to sketching a polar curve by setting the polar equation, solve for r equal to 0. And then solve it using either the unit circle or a calculator. And then also, one thing to note, if, let's say we don't have b greater than a, or b equal to a, like we've had both of those scenarios so far, those were the cardioids and the limisones. What if b was less? We get something else called a dimpled limosone. Let's see what that looks like. So instead, here, what if this was a 4 and this was a 3? All right, we can see why it might be called a dimpled limosone, right? Or sometimes they're called convex limosones. If this is a 2 and this is a 1 or something like that, we get something that looks sort of like a circle with a flattened side. So anyway, whoa, lights went off on me. All right, we get the dimpled limosone that way. So dimpled limosone, regular limosone. All right, so cardioids, limosones, dimpled limosones, these are all kind of in the same family of polar curves. All right, the last thing we're going to do today is a little bit of finding polar zeros. So turn the page once more. We're going to go through example 6. Identify each of the following curves, then find the polar zeros for each of them on the interval 0 to 2 pi. So we're going to first look at 5 minus 5 sine theta. Maybe we'll get a lamp going here. That didn't do much on the screen, actually. All right, maybe we don't need the lamp. All right, 5 minus 5 sine theta. If we look back at our list of different curves and things that we found, 5 and 5 are the same, so that makes it a cardioid. Let's go through and identify them all really quick. 4 cosine theta, that was a circle. -6 minus 3 cosine theta. So we have this one is greater than this one. If you're not sure, you can always graph it. But in this case, when the first one, when the constant absolute value is greater, that makes it a dimpled limosone. And then finally, -2 plus 4 sine theta is just a regular limosone because this value, absolute value, is smaller than the coefficient. All right, so now we know what they're supposed to look like. As we go through finding the zeros of each of these, we'll also graph it to make sure that it makes sense that those zeros would be where we think they are. Starting with the cardioid, we're going to take our value for r, and we're going to set it equal, we're going to set this whole thing equal to 0. So we know first there are zeros at r equals 0. So we're going to take 0 equals 5 minus 5 sine theta. And I'll start by subtracting 5 from both sides. So we get -5 equals -5 sine theta. Then we can divide -5 on both sides. So we get 1 equals sine theta. And then we have to think about the unit circle and go, okay, where is sine of theta equal to 1? Well, sine is y, and y is 1 up at the top of the unit circle at pi over 2. So our only 0 should be at theta equals pi over 2, since that is the only place that sine is equal to 1. Let's try it out. We had, let's see, it was 5 minus 5 sine theta, and lo and behold, we do have a 0, and it's only 1 0 right here at pi over 2. Let's try it with the circle next. We do the same thing. We're going to go 0 equals 4 cosine theta. And then if I divide by 4 on both sides, we still get 0 equals cosine theta. So we're looking for places where cosine is 0. All right, well, cosine is x, and cosine is going to be 0. If you think about your unit circle, cosine is 0 here and here. So that means that theta is going to be both pi over 2 and 3 pi over 2. Let's check it out. R equals for cosine theta. That is a circle, and the circle starts graphing out here at 0. It goes around, and it hits the pole. Sorry, we get a 0 right here, and then we end up here, but we end up back here at pi because circles trace out only in 0 to pi. So if I were to trace from 0 to 2 pi, since we want all of the zeros on the interval 0 to 2 pi, that means I would have to trace the circle a second time around, which is where we get that second 0 from, the 3 pi over 2. Because then when we end up over here, we're at 2 pi, and we've traced our circle 2 times. So that's where the second 0 comes from on the circle. Okay. Well, let's keep going. Dimpled limosone, setting things equal to 0 still. In fact, why don't you pause the video here and try setting the dimpled limosone equation equal to 0 and see if you can find the place or places where this one has a 0, or does it? All right, hopefully you paused it and tried it for yourself. Let's see what happens on this. 0 equals -6 minus 3 cosine theta. So I add 6 to both sides. We get 6 equals -3 cosine theta. We divide by -3 on both sides, and we get -2 equals cosine theta. Well, cosine theta is never -2. Cosine oscillates between -1 and 1. So let's graph it and see what this one looks like. R equals -6 minus 3 cosine theta. As you can see, this one never actually hits the pole. So it would make sense that this one does not actually have any polar zeros. So this one has no zeros. Is it ES or just OS? I don't know. Spelling is hard. Here we go with it. All right, that one has no zeros. All right. So for the last one, the limosone, knowing what those look like, we can expect it to have at least 1 0. Try this one for yourself as well. Pause the video, give it a go, then start the video and we'll talk about it. All right. Hopefully you did. Let's go for this one. Also, 0 equals -2 plus 4 sine theta. So we add 2 to both sides. 2 equals 4 sine theta. 2 over 4 equals sine theta. Or we want to know places where sine of theta is 1/2. All right. So sine of theta equals 1/2. We're thinking about on the unit circle, there are 2 places where that occurs. The first one is in the first quadrant at pi over 6. So we know theta equals pi over 6. The second one is in the second quadrant at 5 pi over 6. These are our 2 polar zeros for that equation. Let's graph this one. R equals -2 plus 4 sine theta. All right, and so we can see this one traces out. We hit the pole here, and then we loop around and we hit the pole again. So these are the right here where it crosses like that. That's going to indicate 2 polar zeros. So that makes sense that we would have zeros there. All right. So that's a bit of an introduction to graphing with polar and some common polar shapes. next time we'll keep going and we'll talk about some different curves and things like that. We'll get into rose curves and all that fun stuff. But until then, hopefully this was helpful, and have a great day.